Yes, let's see this case. The spring shown in the figure is unstretched when a man starts pulling on the cord. The mass of the block is m. If the man exerts a constant force F, find A. the amplitude and the time period of the motion of the block, B. the energy stored in the spring when the block passes through the equilibrium position, and C. the kinetic energy of the block at this position. Now let's consider this case one by one. This is the case of SHM of a system with constant force. Now if we consider a side by side discussion over this part, the first part is what we require in this particular case as the amplitude. Let's consider this block to be of a mass m, spring constant k, pulled up with a force of F. Now at this particular position, velocity is equal to 0 because the system starts from rest, but F net is not equal to 0. So this can definitely be stated as this part is not the mean position. In fact, somewhere around over here, when the particle is at a distance of, let's call it A, from this particular position, the particle will face a force of F in the forward direction and a force of Ka in the backward direction, such that force F can be stated as equal to Ka, or A can be stated as F by K. At this particular position, F net would be equal to 0, so this particular position becomes the mean position. And if this is a mean position, velocity over here would be maximum, which actually gives us a lot of detail about this particular position. So basically this position becomes the mean position, and the position where the velocity was equal to 0 becomes the extreme position. Hence the amplitude A, which we need to consider in this part, simply comes out to be equal to F by K. And the second thing is time period. Time period is independent of the initial situation, that comes out to be 2 pi under root of m by k, which is the first part of this particular problem. In the second part, we need the energy stored in the spring when the block passes through its equilibrium position. U of spring is required in the second part when the block is at equilibrium, and the state where the system is in equilibrium is termed as mean position. Now if you consider this thing over here, the system is in equilibrium when the body is at mean position, and from natural length it is at a distance of a. So U spring can directly be stated as half of k of a square, because the extension in this particular case would be equal to a. So this can be stated as half of k of a square, where half k can be written as such, and a can be written as f by k as calculated in the previous part. So the result comes out to be f square by 2k. That is the answer to the second part. In the third part, we need the kinetic energy of the block at this position. Kinetic energy of the block at this position, which we call as mean position. Now we very well know that the velocity at mean position is actually equal to a into omega. So V in this part can be written as a omega, where a can be written as f by k and omega can be written as under root of k by m. I'll write the terms as such. I'll change this thing at a later on stage. So the kinetic energy of the system can be written as half into m into v square, or half into m into v square can be written as f square by k square into k by m, where 1k and 1k would get cancelled and 1m would get cancelled, and the result again comes out to be equal to f square by 2k, which is the answer to the third part in this particular problem. Thank you.